Dang. Really? I think what someone pointed out to me was interesting. It was like, I think it was at the end of last week. We had 4 or 5 weeks left, but only 2 or 3 of them were full weeks. Because of the weeks we have left, there are 2. Yeah, there are 2 Friday weeks. Oh wait, actually, I think there are 3 4-day weeks because we end on a Thursday.
Yeah, 2 around Easter. Yeah, time goes by quickly at the end.
How many full weeks are left? Are the Easter weeks and are the last 3 weeks of the semester 4-day weeks? Like Easter, the 4-day. Wow.
This is the best thing ever. Okay, maybe not the best thing ever.
Good for us though. We don't miss any probability.
We don't miss any Tuesdays. Just Monday, Wednesday, Friday.
Okay, so a couple things. I'll turn off the extra overhead. So bright. So just a couple of comments on homework 9. And then we'll talk about the project. The project is one of the last things to do. Very flexible in what you look at in terms of topics. Talk about exam 2. Exam 2 is next Tuesday. So 4, 9, 19. Thursday, I have not posted any study problems yet, but I will. On Thursday, we'll do some review from that, go over different problems and things like that. Today, we'll kind of go over the outline of things that are on it, right? And then we'll talk a little bit about transformations. So, and moment generating functions. Kind of wrap up what we're going to do in material in chapter 6. And I will post. I'll get the homework aid finished. I almost finished grading it, but just kind of mistimed things a little bit. But we'll get it graded and get it back, and we'll be able to see that one as well. So on the homework 9, the last question is about a multinomial. And there's 4 time periods. There's the 4 seasons. And percentage of births, I think it was 24, 24, 26, and 26 is the probability of being born in the 4 different quarters. And the question asks, what's the probability if you have 4 individuals? What's the probability that none are born in the last quarter, winter? And it lists 3 things you would consider, because if there's none here, then the others have to be split there. And so when I wrote out the counts, I was really had in my mind that it would be not in the winter, but there would be some of those 4 in the other ones. None in the last quarter, so this should really be modified, but some in the others. And the way that can happen, if you have to have at least 1 in each of these, and there's 4 overall, that means you're going to have 2 in the first period, and then 1 in the next ones, and nothing here, or maybe 1, maybe 2 in the second period, and 1 of those, each of those, and nothing there, and then or 1, 1, 2, 2, and 0. So in the problem, I list those three outcomes, and so I was thinking about, that it's not in the last quarter, but some in the others, right? If it's none in the last quarter, right, they can all be in the first or all be in the second, and then there's a lot more possibilities to enumerate. And I was just thinking about this more restrictive case there. Right? So that when you get to looking at that one, hopefully that will help. It makes it not such a big enumeration, that would clarify what it really means. But any questions about another question, there's a simulation. And the way the original book is written is they say that P, say in a binomial situation, if the data that we're going to see is binomial, it says as a distribution on P, they say to make it uniform between 0 and 1/4. Well, in the original binomial model, the range that P can have generically for that model, it's possible, is all the way between 0 and 1. But it wanted a distribution that's uniform between 0 and 1/4. In Bayesian statistics, so X is the number of count. In Bayesian statistics, we're often interested in looking at the posterior distribution of P given X. Well, if the prior distribution, the distribution on P, restricts it between 0 and 1/4 and 0 everywhere else, there's no way that you can ever get any probability outside of that interval. Right? The calculation that goes for in Bayes' approach, we would look at the density of P given X. Well, that can be written as the density of P times the density of X given P. That's both of them together over the density of X. And if that distribution on P is restricted to only part of the parameter space and 0 other place, well, it's still 0 elsewhere. So if P is uniform from 0 to 1/4, then this density given X can be greater than 0 only if 0 is less than 1/4. So if we happen to get, X started having a lot of successes and it looked like it was really likely that P is bigger than 1/4, there's no way for the distribution to adjust to the conditions because of the strict assumption that P doesn't ever go outside of 0 to 1/4. So the point of this problem is that, well, that's not, that also creates some bit of difficulty. You're not integrating from 0 to 1, you're integrating from 0 to 1/4, and that makes that a particular integral a little bit messier. So if we instead say that P is distributed as a beta random variable with alpha and beta as its parameters, well, this distribution has support on the interval 0 to 1, so it's not going to artificially restrict it at all. And you could choose alpha and beta to match the mean and maybe match the coverage, so most of the probability between 0 and 1/4 as an alternative. So you can make it look very much like this or kind of like that, right, without doing that artificial restriction in the range. One problem, it's which one? To ask what's the probability that P is less than 1/4, and I mentioned that I would get some R code to do that, but I didn't have any R code written down there to do it, right? But with the R and simulation, you can get it pretty quickly. So this is what this looks like in this part G. What was the probability that P was less than 1/4 for that beta distribution? There's a couple ways to get it. This was the simulation code here to run. So if I just grab all that and plop it in there, it will run. it will simulate, we're going to do 10,000 simulations from this distribution, and these are the alpha and beta I say to use. So this line in here generates 10,000 values of p from that distribution. So what percentage, so those values of p, say the first 20 values look like that. Some of them are less than, well, most of those look like they're less than 1/4. Out of the 10,000, how many are less than 1/4? So if you write down p is less than 1/4 in R, that will return a true value every time p is less than 1/4, and a false value every time it's not. And when it says add those up, it counts true as 1 and 0 as, and false as 0. Right? So, you know, if we look at what those, say we take the first 20 values here, right? Well, those are all true. They're all less than 1/4. And if we add those up, you know, for those first 20 of them, all 20 of them are less than that. But if we do that for all of those, it's out of the full length of 10,000, right? The sum there. So 9,858 are less than 1/4. Right? So if you divide that by the 10,000, and b was 10,000, you get a probability. So, there's also a p beta. Right? So if you help p beta. There's a beta distribution function. There's a density. This p1 is the cumulative probability, right? The probability you're less than a value. Right? So you can put 1/4 in there. So we can put p beta 1/4 in there. And for that one, you know, not based on simulation, but more of an exact calculation. It might be an approximation to the integral. I don't know if we can actually do that integral with the, I call them alpha and beta. I called them alpha and beta here. Alpha and beta, put that in. That'll give you a probability. And it's not much different from the simulation with 10,000. So this command here, that little line is missing. But that's a little bit more what's going on with that problem, and a little bit how to go that. Right? Just as a side, you know, there's another way to get that number, right? If you add things up and divide by the number of trials, that's the average. So you could just type the mean of p less than 1/4, and it would give the same thing, right? So if you count up all the numbers and divide by the total, that's the same as averaging. So anyway, so that one little extra command or a little more details for that one little part of it. That's what's going on with that. Any other questions on the homework? That one's due on Thursday, and I'll post solutions pretty quickly after that one. So. Okay, so that's a little bit about the homework. Now this project, right? So the project is an opportunity for you to investigate something you're interested in with probability, explore a topic a little bit more, and then write something. So, you know, probability can be used very, very mathematical, it can be a lot of equations, but if you want to communicate something about chances and how it's used and how it's applied, and how it relates to data or something you're interested in, right? Then putting it into words is important for communication. Right? Whether you go into a very technical field, you write papers, you write reports, you write articles, and so communication about very technical topics is something that's good to develop. So the projects are probably a little bit more work than a single assignment, maybe like a couple assignments worth of work, but it's not huge, right? It's not a 30-page paper or something like that. I say here just 3 to 5 pages, you know, something not shorter than that, but if you're, many people will possibly go beyond that, if they're writing out formulas, if they're doing it on the computer and have any output and, you know, graphs and things like that. So there might be a few extra pages that have some output, kind of like an appendix or something like that. You can work in pairs for projects. If you want to do something in common, then the projects are typically a little bit longer. You explore things a little bit more. Maybe there's a way for each of you to do part of a problem and then combine them together so they work together, but there's kind of independent work. Right? So you can look at theory, applications, simulation, historical context, or any other angles connected to probability, investigate it and write it up for this. Right? So there are a number of internet sites out there that talk about probability. For instance, there's a National Institute of Statistical Standards engineering handbook that has some probability content in it. And a number of these will not only be very basic introductory probability, but more advanced topics. So you might find something there. The third bullet point there is Journal of Statistics Education. It's an online journal through the American Statistical, see if JSC, no, right? Oh, Jamaica Stock Exchange, no, that's not. The Journal of Statistics Education is an online free journal. You can look back through ability. There are a number of probability of a KISS, right, or a probability of different language of conditional probability. Many of these are aimed at teaching probability at either this level or at an introductory level or maybe a high school level. But they often do research about the subtleties. We'll describe the subtleties behind some of that particular problem. So maybe there's an interest there. If you are in math and with education as a major and would anticipate teaching something like this at some level, you could write about a lesson plan or an approach to teaching some of these concepts or incorporating some of these concepts, maybe simulation, maybe something that would be a little bit beyond the standard curriculum for middle or high school students. It's possible to look at something like linear regression. So there's there's a probability model under there that says the data errors are normal. Those are described in elementary statistics textbooks. If you took any of our versions of intro statistics or taken it someplace, you've probably seen one of those, or there's some books in the library and other places. So in that, you describe the model. You can think of your audience as other students in the class, where you don't need to say exactly what you don't need to go back to first basics, but what's the expected value of a response given an X value, what's its variance, a few other aspects of that. If there was a part, we haven't done all the problems in the book, of course, so you could take a group of problems or an area, if a particular kind of area was interesting, and write a summary. So you might use that to organize some information. We haven't put things together, so we'll talk a little bit about moment generating functions today, but we certainly won't be comprehensive, so you might put together a bunch of results and describe them and put into your own words a summary. Eventually we'll talk about central limit theorem. With that, there's possibility of simulating a lot of things, right? So there's the simulate central limit theorem or other limits. How big of a sample size do you need for it to work? How do you demonstrate that it works? Well, besides mathematical proofs, which are going to be beyond mostly what we're going to do. There's some books, if you're really interested in it, that give some proof about that involving moment generating functions, so you might be able to investigate the theory a little bit on that. But if there's a data set, you sample, get a population data set, you could write a little code in R to take different random samples of different sizes, look at the sampling distribution of the mean, compare it various ways, and see if the central limit theorem seems to, how is it affected by sample size or shape of distributions and things like that. If there's a game of chance, poker, roulette, other things like that. You know, you can figure out some probabilities related to that, or expected values, or talk about strategies. Some games, if they have many, many steps, get a little bit, you know, involved in terms of actually writing out probabilities and chances. So maybe taking it to a game in a certain setting and looking at the chances of the next move, or something like that, or things like that. Those could be probability calculations, maybe a simulation, and so on. Different tournaments. You know, March Madness is going on. There's a bracket. There's kind of team ratings behind those. What's the chance that a certain team would progress all the way through? I mean, assuming that you have probabilities, you know, turn those ratings into probabilities that a team wins. You know, there's a lot of different ways that it can go about getting to the next status, or you know, like in a World Series of baseball, it's a best of 7 games. What's the chance that it goes 4 games, or 5 games, or 7 games? What's the expected number of games? You could describe that probability structure. And then, you know, if the teams aren't evenly matched, they're on unequal probabilities, or the probabilities change as things go along. You know, it can be 1 or 2 variations. You see how probabilities are influenced. Or if there's some other application in society where there's chances, whether it's stocks, or weather, or economics, or something else, or voting, that you can be there. On the back are a few other ideas. There's a few sections in the book that we didn't cover, or won't cover as much in detail. The idea of a project in that would be reading that section, maybe looking at a couple of the problems associated with that, and just writing your own summary. And this might come from this book, or if you've econometrics, or have an application in engineering class, or some other thing that had some probabilities associated with it, it could be adapted. Another possibility is to do a biography of somebody in probability and statistics. Probability for this class. And so, you know, back on March 15th, I sent out, you know, an announcement that our book has historical information, which is interesting, and, you know, because that's part of the development of the field, but of course not all of it. And there's many sites that talk about, you know, women in statistics. You can find different individuals, race, ethnic groups that are not as represented in the longer term historical presentation. Finding out about somebody, what do they do for degrees, what they worked on, what are they involved with. You know, there's different. So anyway, that it would be possible to do a biography of somebody, learning a little bit more about the areas that they did. It might take some, you know, a little bit of searching, but some of their articles and areas would be related to probability topics that we've examined, and so that would be a possibility. So it's pretty wide open. Over the next few weeks, you know, next couple of weeks, you know, as you're thinking about you know, maybe something maybe strikes you as, oh, I would like to do that. Well, you know, start thinking about it. If it's a little bit less clear what you might do, think about these things. You want something that's feasible, that is, you know, have enough content. You know, really, once you start digging into something, it can take up the 3 to 5 pages with things pretty quickly. But we can meet, right, office hours or other times. We'll probably try to schedule some extra time, primarily after Easter, to get longer periods of time that, you know, you need to talk about projects. And as you write it, you know, there's just a little note there that it's good to have an outline structure, you know, a title for what your project is, a little introduction, saying what's the big picture, what are you trying to talk about, you know, a little bit of focus on the probability statement, maybe some elaboration that could take the form of simulations or computations or working some problems, And then, some summary, kind of wrap it up. What have you looked at? What have you learned by doing the project? And how would it fit in reference to the broader course? That's the idea of the project. So, any questions or about it at this point? But go take a look at it. I know we have a bunch of stuff going on, but hopefully this is enough lead time to think about ideas, mull it over for a little while, and then spend some time over the course of a couple weeks putting it together. So. All right. So that's about the project. Looking ahead to what's on the second exam, we've covered a number of things. The second exam will focus on homework, 6, 7, 8, 9. Those are the 4 homeworks we've had turned in since the last exam. These 2 really focus on chapter 5, and these 2 are focused really on chapter 6 material. Right? And so the exam will focus on those. For the exam, you can have a page of notes. You can use 2 sides. For that, ordinary 8.5 by 11 page. The number of formulas, distribution, some methods of dealing with things. You can write down whatever you want. So you can organize your information there. Calculator. There'll be some things where you'll do numerical calculations, so it's good to have that. Homework 6 was in chapter 5, looked at continuous random variables. For those, we had a density function, the cumulative distribution function, so PDF, capital CDF by its names. We also looked at calculating the expected value, or the expected value that's squared, turning that into a variance. Maybe the expectation of something else. This one used as specific examples. Uniform random variable. Between two endpoints, 0 or 1 or something else. I looked at exponential, random variable, and beta. Was on that one. So, with those particular types of distributions, we asked what's the mean. So some of it was applied, right? Here's 2 values, what's the mean, what's the variance, standard deviation. And some of it was, show me that the mean is alpha over alpha plus beta. Or for a particular case, if alpha is 2 and beta is 3, what's the density? What's the expected value of some function? So there's a little bit of, a mix of application to a particular topic and calculating probabilities. And some of it is, showing the intervals to show how you get the means, the variances, or some stuff like that. Homework 7 was also on this chapter 5. So, but it focused on the gamma random variable, its parameters, normal. For the normal distributions, we found probabilities under the curve and percentiles. believe I will give you a normal table. So if you can look up anything in a normal table, but I need to kind of flesh that out to see exactly how that would go. Right? Normal, and it has some things on moment generating functions. Finding moment generating functions for, not only these variables, but things like exponential was one that worked out well. Right? What do you do with the moment generating function? Take a derivative to find means, maybe transform the variables. We'll talk a little bit about that more at the end, the rest of today, but it had some of those. But both of those were in chapter 5. Topics. The homework 8 was in chapter 6. They considered bivariate distributions. So 2 discrete variables at a time. Mostly that was, displayed by a table of counts somehow. Right? We had continuous. So P of x, y would be probabilities of the combination of events of x and y. Continuous bivariate distributions as well. That would be this joint density of x and y. Right? So if you had 2 variables at once, that was the joint density. We could take a sum or integral over one of them to get a marginal, and then we could look at conditional distributions, f of x given y, for instance. And figure out what those things were and maybe see how they're changing with the different values. We could take the expected value of a function of 2 random variables. When it was expectation of xy minus the expectation of x times the expectation of y, that was the covariance. And we also did correlation. And the covariance divided by the 2 standard deviations. We looked at that a little bit. In there was the linear transformations. You take x plus y or x minus y, and they're correlated, right? Then their variance wasn't just simply the sum of the variances. There was that covariance term that affected things. Right? This linear transformations works for any sorts of type of linear transformations, averages and other strange things, but we can stay with those 2 as primary examples of how it gets used. And then homework 9, which you're working on, in chapter 6, has things with conditional expectation. If you have a conditional density x given y, you can take the expectation of x, given that y is some value. As y is changing, maybe the average value of x is changing if they're related to one another. And then we got marginal expectation variance via conditioning. And those are the 2 results that you use here. The expectation of a random variable x is the expectation of its conditional expectation. Right, and then the variance of x from a similar thing. So it's the expectation of the conditional variance plus the variance of the conditional expectation in a model with things written as a marginal of 1 and then a conditional distribution of the other ones. did a little bit with Bayes' rule. It comes up in this homework as we're figuring out marginal, integrating out P from an equation to get to the marginal distribution of X. So it kind of follows the same pattern as doing that. And then lastly, multinomial distribution. So if there's a question related to each homework, maybe 2 questions from some homework, it's about 6 questions. In an hour, or in the hour and a half time. So try to write it as usual, so there's time to think about it and write more and explain more for things. But that would be kind of scope of the topics, right? Are there any questions about the plan is to get some study problems, and then work on some of those problems on Thursday. Have some other material you can look at over the weekend to study. The exams are on Tuesday, so if you're studying and have questions over the weekend, email or things like that, or have office hours on Monday to go over some things. All right. So we've done 3 parts today, where we had to talk about the homework and then the projects and this. And I wanted to say a little bit more about moment generations, and as we move into what we're going to go into is chapter 7 on transformations. Moment generating functions and a transition to chapter 7 on transformations. The general problem with transformations is you have a bunch of random variables. You have a bunch of random variables, say in random variables. Maybe they're independent, maybe they're not. And we're interested in some function of them. And where G is some function. And then the question in probability is, what's the distribution of Y? Is it a random variable we recognize? Can we tabulate its probabilities or show its probability somehow? Can you tell me its mean, its variance, other things about it? By this function, so a number of examples we could think about. So, you could, Y could be the average value of X. So our function, could be, we're going to add up the Xi's and divide by the number of cases. That could be the thing. Y, other multivariate summaries, we could take, be interested in the sample variance. We could take things that are a little bit more complex as functions of that. What's the distribution of the variance? Instead of taking the average, we could take the median. Right? Why the function could be, doesn't have to be a linear function, a continuous function. The median is discontinuous, right? So as the values move, a few of the values move, the function doesn't necessarily change. But as soon as one value moves very much, then the median then it kind of jumps to that value. So you could do median, you could do other percentiles, Sometimes these things are called order statistics. Minimum, second value, maximum, middle value. Order statistics would be another name related to the percentiles. Those would be ones involving a lot of the different variables. Sometimes our functions, maybe we only have one or two variables that would be of interest. So some simpler examples, if we just had x1 and x2, we could take just the sum of those two things, or the average, or you take the difference of them. What's that random variable? If we just have a single random variable, we're going to start with most of the case of we have a single random variable, we just change it somehow. We take the square root of x, or we take the log of x, or we do like 2 pi x squared, right? So if x is really a radius, and we're then calculating the area, what's the distribution of the area rather than the radius, right? And again, what is this, right, the distribution of y, which is probability distribution. We figure it out. There's 3 different ways that we'll learn to do this. The other thing that goes on, if we have some function involving a bunch of random variables, we will ask questions in terms of what happens to y, what happens to the distribution of y as n goes to infinity. Is large. So sometimes, so the mathematical side can say as n goes to infinity, think about doing that. In terms of a practical side, you don't have an infinite sample, but if you're surveying 5,000 people, that's a pretty big number. Does there anything happen to the distribution of this thing as n gets big? Right. So things like y equals x bar. This question is the focus of central limit theorem. And there's many, many interesting relationships that as the sample size gets big and you're adding things together, taking averages, distributions that were at one type start to look like other ones. They become looking normal, they start looking continuous, and so on. And so that's kind of we can't figure it out exactly by figuring out the probability density. Sometimes there's a limit or an approximation, a large sample thing that happens. And so we'll see a little bit more about that. So one way that we can do some of these transformations we've seen with moment generating functions. So the first transformation that we've talked about involves moment generating functions. That's called the moment generating function method for transformations. At the core of this is a theorem. We don't prove it here, but if the moment generating function exists near t equals 0, right, then mx of t is the moment generating function of a unique probability distribution. Which is a way of saying that two random variables that are different don't share the same moment generating function. And so if you have that moment generating function, there was a distribution that matched to it. Right? And so you can write down many functions and call it a moment generating function, but does it actually correspond to a particular probability distribution is kind of another question. There are people that write about distributions talk about families of distributions. That certain groups of distributions are characterized by a few parameters, and there's something in common among these. If you change the mean or change the variance or change the parameter in some way, it still has the same functional form, and people talk about that being in a family. So the relationship between the parameters and the means and variances and probabilities has a certain pattern that are there, right? And so some of the main type of families of these, so normal, for instance, that if the density function for a normal has 1 over 2 pi sigma squared down here, and e to the negative 1 over 2 sigma squared x minus mu squared. So if you change the mean or standard deviation in here, it's going to be the same. This is the the bell-shaped curve centered at the mean. Right? And so you can change the mean and standard deviation or variance, right? And it's kind of considered to be in the same family, right? Well, let's just take this one as an example, as a relationship to the moment generating functions. Sometimes so x is normal with this distribution, and y is a linear transformation of x. Well, it turns out that y is still a normal random variable, that the probability distribution is still within this normal family, and it's just a location scale change of that. One way to show why that is still in the same family and what happens with the transformations is with moment generating functions. So for normal, if x is normal, mu variance sigma squared, moment generating function of this one, e to the t times mu plus there's a t squared sigma squared over 2. That was the moment generating function. We saw that one time, and it's in the book. It's a little completion of the square thing to make this thing work out. So now we take y equals a plus b times x. In general, what's the moment generating function of y when we do this? Or the expectation of t to the y times t. That's what this means to do. And you put in e to the now a plus b x, you put in what that is in there. That's fine to do. This is an integral. Also, if you multiply that out, there's the e to the at part. It does not involve x. So this expectation is with respect to y. This one's actually with respect to x, meaning that this is an integral dx. This one is an integral dy. They happen to be the same, and that is different calculus to really kind of make sure that works out what it does. But with respect to x, just e times at, when you spread that out, there's no x there, and it's multiplicative. So it just come outside of the integral, come outside of the expectation. And then there's an e to the e b xt. And so that's grouped together just a little bit differently. X, and group the b and t together there. That looks like the moment generating function of x with bt stuck in that argument there. Slide in here, slide that. So the point is showing that's, so in general, that's the relationship to the moment generating function. And when you have this one up here, right, we put bt there, there's a bt into that one, so there's b squared t squared. And you can regroup everything so that it looks, again, like another normal. So the moment generating function of y, once you go through that, just gonna have to write it down for space. Well, there's an e to the at, that goes there. And then there's the other part here. Also some space. There's a t times mu, so it's bt times mu. And then there's a t squared, sigma squared over 2. So the sigma squared over 2 there. T squared now becomes b squared t squared. And if you put all that together in a nice normal form, it looks like a plus b times mu, right, times t. Find this term and that term there. Plus, I wrote it with t squared. And then b squared, sigma squared over 2. So here's e to the something times t plus t squared times that. That looks like the normal form of the MGF. And because of that uniqueness, then y is normal. Its probability density is normal. The means and variances are updated according to that formula. So by that uniqueness, so y is distributed as a normal random variable. After that scale change, the new mean is a plus b times mu, and the variance is b squared sigma squared. Because there's that correspondence within the families for MGFs, it is normal again. One component of this is the range of support, right? So x is the whole real line, and the linear transformation still keeps the whole real line, so that matches up as well. But this works with other families, right? So, as a second example, say x is exponential. The density for x is 1 over theta e to negative x over theta. And this parameterization is exponential of x is theta, and the variance of x is theta squared. The moment generating function for this one is 1 minus theta t negative 1. And this density, importantly, was when x is greater than 0. Or we can consider different transformations. If we do that same linear transformation, are we going to stay in the same exponential, or the same exponential distribution family here? If you do a linear change like that for some arbitrary values of a and b.
No.
Be something, going to switch it a little bit, right? There's a little change, right? That what goes. How are things? Is y strictly exponential something? Does it have an exponential distribution? I mean, look what happened if we did this, right? The moment generating a function of y, there's an e to the at that gets out there, right? We did that in the general case before, because you're adding something, you get the e to the at there. But b multiplies x, so you get 1 minus theta bt to the negative 1. So this looks like a new parameter, but there's that extra thing stuck on there. There's this, right? So there's this extra part of the moment generating function there. And so it's not exactly y is not exactly or strictly exponential unless so if x is greater than 0, right? Adding something on there, moving everything over away from the 0 point. It's not going to be starting at 0 anymore. So it's just not going to be exponential. We would need for it to stay exponential and stay in that family. We would have to not add anything. You can't shift it over. And we'd actually want b greater than 0, right, to have the y values be greater than 0. Some applications you might have a negative slope, negative multiplier, as long as b is positive. If that's the case, so if y is just x times b, or b times x, I guess, right, well, with b greater than 0, right, then the moment generating function of y is simply 1 minus theta dt, and here's our new parameter. So y then is exponential with parameters theta and b. And so we would know that the mean is theta times b, and the variance is theta squared b squared, and we would know the cumulative probability distribution because we know that general form for an exponential, and that's the result. This one is not hard to do. We will do this one with something called a CDF method or a PDF method. Right. This one is not hard to do to figure out what that distribution looks like from any of these other two methods that we'll do, but it's not exactly exponential if you're shifting everything over. Right? So there are. Chapter 7 then gives kind of the full range of, a few different methods for dealing with that, and we stay in the form there. Right? Can you do, so, yeah. But any questions about it? So, the other moment generating function type of thing that we've seen, right, that if x1 and x2, let them be our independent random variables. And we let y equal the sum. Then the moment generating function of y ends up being the moment generating function of the first one and the moment generating function of the second one. And if x1 and x2 were random variables, we knew their moment generating functions, and we multiply them together, and we see that it kind of sticks within some family of moment generating functions, then this would be one demonstration that y has a certain distribution. Right? So for instance, if x1 is binomial with n1 trials and a probability of p, and x2 is binomial with n2 trials and the same probability p, and they're independent of one another. So you sample a number of people in one county, and you sample a number of people in another county, and you count the number who are registered to vote, and a certain voting rate or registration rate in one county, and across the other county next door to it, it's the same, and you add it all together. What's the distribution of the total? So we have y equals x1, x2, y what is it? The moment generating function of this one was p e to the t, that'd be p times n1. That's the moment generating function of this one. The moment generating function of this one is that, right? So the moment generating function of y, so the product of those two things. So what's this thing? P e to the t plus 1 minus p n1 plus n2. Adding binomials with the same probability, right, keeps it in that binomial distribution of families. And so y is a new binomial. Right? So y is binomial in 1 plus n2 times p. So it's a new binomial. There's other ways to show that or think about it. Right? If x1 is a sum of n1 trials with a probability p, and then n2 is, x2 is just the sum of n2 trials with a probability p. Right? Altogether, there's n1 plus n2 trials. They all have a probability of p, and that's binomial. So there's a couple ways to look at it. But the moment generating function business, right, does that. Is it important that p1 and p2 are the same? P1 and P2 are different, you multiply these together, you don't get just one thing that looks like it's a more of a mixture, right, of things. Right? So in this case, the probability distribution will be binomial, will look like that. If P1 and P2 are different, you can get different things, right? So we could even look at that a little bit with simulation. Right? So let's say that x1 is, we can do random binomials. Maybe I'll try to get this up to the, can't really get it up to the top of the right. That can get it up to the top. So if x1 is a random binomial, let's do, say, 1,000 iterations, 1,000 different samples. And let's say we're going to take samples of size 50, and one group has a probability of 0.3. Right? So here's the histogram of x1. The probabilities kind of look at like that. 30% of 50 is around 15, so it's centered like that. Now we have another group, R2, with 1,000 random values again. Sample size 50 there, but if the proportion's different, let's say the proportion is 0.6. The histogram of x2, right, is going to look like this, kind of shifted up there. If you combine them, and I can put these things together. So x1 plus x2, right, adds them together. So it's going to add the 1,000 values to the corresponding 1,000 values entry by entry. Right? It's going to be out of 100. It kind of looks like that. It still looks, let's see, in class, this n here means the number of bins. So some were centered at, well, but kind of normal-ish, but it's not actually. It actually has a different variance and spread. It's kind of a little too flat in the middle because one group was kind of smaller and one group is a little bit higher, and so it's a little bit off. So we could contrast that. So let's say y is x1 plus x2. And then the y that's actually binomial, y again binomial. We take a random binomial 1,000 times with a sample size of 100, right? Because x1 plus x2 has 100. And we kind of just average those two, right? 0.3 and 0.6, right? Half of them 0.3, half of them 0.6. So that'd be like 0.45 on average. That's kind of why that's near there. Right? We could plot y versus our binomial ones. Okay? But they're random orders, so if we sort them, it's kind of a probability plot, right? So the sorted values of y versus the sorted values if we take actually from a binomial, And this thing is, well, they're discrete. Wow, it's coming out pretty close. I know it's not exactly binomial, but where is the extra? What's the mean? The means are going to be about the same. So the variance of y is that the variance of y binomial is a little bit bigger. It's not too different, I guess, in my samples.
If we increase the disparity between the probabilities, would be more likely to see a difference.
Yeah, I mean, that's exactly it. So there's a slight difference here. So let's say x2 now instead of this is 0.9. Right? Then we add them together. Right? The corresponding thing here is not with 0.45 anymore. So 0.3 and point for half of them, 0.9 for half of them. Midpoint is 0.6. And then we plot the sorted values. What are we going to see? It's so discrete. So let's see. The variance of y binomial. That looks pretty different. And so if we do it on a standard deviation scale, is there's quite a bit of difference. There's less standard deviation for this one that had some small and some big. They tend to add together and get kind of average. Whereas the single binomial around 0.6 had more variability. So that wasn't an elegant demonstration, but it's not exactly binomial. And if it's too far apart, then you really can see it, and it's more extreme, right? But if this was P1, if this was P1 and this was P2, multiplying those two things together, it just is not a binomial. So it doesn't have a binomial distribution. And if P1 and P2 are far enough apart, probably that interacts with the size of n as well, then it's not going to be approximately binomial. You can have more variance if they're different. Right. The one thing I wanted to, so if you have independent ones, you can add them up, and often you get things staying in within a certain family. Exponentials, you can't add exponentials and stay in the same family. But the gamma random variables had 1 minus beta t to the negative alpha, so that if you have a gamma random variable with alpha 1 beta and another one, if that's x1, and x2 was a different gamma random variable with alpha 2 beta, and you add those together, then the density of x to negative alpha 1 plus alpha 2, if you multiply the moment generating functions together. And this one quickly can be seen to be a gamma random variable where you add the alpha there times beta. So exponentials doesn't work because it had to have a negative 1 up here. It's very strict. It's just this decreasing. But gammas is kind of a bigger family. It has 2 parameters instead of the 1. An exponential is a special case. So adding independent gammas with the same beta value there stay in that family. So there's other examples that work out nicely for the transformation. And so in this, right, I want to explore one thing, right? Why do they have to be independent? What does that matter? So let's say y equals x1 plus x2. In general, what's the moment generating function of y? this thing can be written as an integral, over e to the t y, f of y, dy. That's what it means to take that integral. What we've done in the version that didn't involve x is I write this thing as expectation of e to the t x1 plus x2. If I want to write that one as an integral, right, now there's two variables involved. Right? This would be an example of a bivariate function, a function of two variables. We're taking the expectation of something. Right? With x1, x2, we're interested in expectation of e to the t times that. We're interested in that little function. How do we get that expectation? We have x1 and x2, so it has to be a double integral. E to the t x1 plus x2 as values. When it was just y, we had the y density here. There's two variables which have the joint density, right? x1, x2. dx1, dx2. So what can we do now? If x1 and x2 are independent, if x1 and x2 are independent, the joint density, what was the definition of independence? Then you get the multiplying of the two marginals. Right? So there's an integral here, e to the tx1. I'm going to multiply this out too while I'm at it, tx2. Split it. By independence, this is the x1 density times the x2 density. dx1, dx2. What can you simplify that? Some things involve x1, some things involve x2. Everything's multiplicative. And there's no case where there's an x1 and x2 bound together in some function you can't separate by multiplying. Right? So in calculus, you can pull all the x2 information separate from x1. And so this thing can be written as do this one, x1, f of x1, x1, e of x1. You can put that all together. And everything x1 doesn't involve the x2s. And everything x2s doesn't involve the x1s. And so that double integral under independence with this particular x1 plus x2 function splits. Right? And so what are both of these things? Those separate ones. Those are the moment generated functions. So when we've been using this and saying that they had to be independent, the independence works right at this point there, right? And allows us to factor into these two things. Right? But so anyway, that's why independence is important. If they're not independent, then you can't factor this density. You can't factor this density. You can't split it across the two integrals, and it's a more complicated thing. It still exists, it's still something you could do, but it doesn't work out quite as nice. In general, if y equals some function of x times x1 times some function of x2, and x1 and x2 are independent random variables, then the expectation of y is the expectation of that function, which is a double integral. But because it's multiplicative there, and if it's independent, it can also be split, right? So it can be the expectation of g of x1 times the expectation of h of 2, whatever they are. So the expectation of x1 times x2, for instance, if they're independent, is x1 times x2, which ends up meaning that the covariance between two random variables, if they're independent, is just 0. Because the covariance is that the expectation of that product minus those two. And if they're independent, then they cancel, and it's just 0. So independence kind of factors it in a special way with moment generating functions and sums. And so that's a bit of a preview, right, of taking a couple random variables that you know something about, adding them together, or doing a linear transformation, scaling them maybe, and then figuring out what the new distribution is. And this worked for some things. Even in that, what appears to be kind of an easy case, you take an exponential, you add something to it, it's shifted away from 0. It's not exactly exponential anymore, so what is it? When we do transformations more generally, well, a couple ways of figuring that out. So we can write down exactly the probability distribution, calculate the probabilities if you're above a value or below a value, and then do things for means and variances. So homework is due on Thursday. On Thursday, we'll do more review problems, talk more in detail about material for the exam, ask questions. I'll try to get something posted. If I get it posted early Wednesday, it'll be a day to kind of look at it along with the problems and review things, to think about it, get questions for that time. Do what is convenient for the schedule, I think, Or, closer to the Wednesday.
Right.
Better, but, if you're really getting ready for something on Wednesday, something in that morning that goes skiing. But, during that Wednesday, Thursday, Friday.
Yeah, okay, cool.
Yeah.
I will. Thank you.
Okay.